This is the video for our paper, Learning Foresightful Dense Visual Affordance for Deformable Object Manipulation. Manipulating deformable objects is an important yet challenging problem in computer vision and robotics. The difficulties come from many aspects. Taking unfolding cloth as an example. First, unlike rigid object manipulation tasks, manipulating deformable objects usually requires multiple steps to accomplish. Additionally, most actions can hardly facilitate the tasks, due to the exceptionally complex states and dynamics of deformable objects. Most importantly, some local optimal actions make the object temporarily closer to target, but making following actions harder to complete the whole task. In contrast, global optimal action will provide more opportunities for future actions to finish the task swiftly and smoothly. In order to tackle the problems mentioned before, we propose to learn dense visual affordance for multi-step deformable object manipulation. Each point in the picking affordance represents how good the picking point is for performing the tasks, while each point in the placing affordance indicates how good the placing point is, conditioned on one specific picking point. This representation could model complex state space and large action space. And with awareness of future actions, the proposed affordance could empower the agent to select global optimal actions for tasks. To clearly illustrate our framework, we first introduce how to use dense affordance to represent a greedy manipulation policy. Given a picking point, placing affordance reveals how good the placing points are, conditioned on the picking point, and score of each point in placing affordance can be estimated by the result of the corresponding pick and place action. Picking affordance reveals how good the picking points are, and each point score of picking affordance can be estimated by finding the best placing point conditioned on that picking point. In other words, the maximal value of placing affordance conditioned on that pick point. The greedy method leads to local optimal states for deformable object manipulation. Some states may temporarily have larger coverage area, but make following actions hard to collaborate and accomplish the whole task. To tackle the local optima problem, we introduce the concept of value to indicate whether a state can facilitate following actions to accomplish the whole task. Value could be estimated using the best outcome of all possible following actions performed on one state, and all following actions start with picking. Therefore, value could be computed by the maximum value of our picking affordance, because the picking affordance reveals the capability of all possible picking actions for further fulfilling the task. Then, each point score of picking affordance can be estimated by the maximum value of the placing affordance. Finally, placing affordance should be computed by both the coverage area and the value of the state after executing the placing action. As we can see, the supervisions among value, picking affordance and placing affordance form a dependency cycle. We break the dependency loop by training in a stage-by-stage manner, from states close to the target, to complex states. We replace the value of states in the last step by its coverage area since those states are very close to the target state, and their values should be close to their current coverage. With this key assumption, we can train the whole model by first training the placing affordance of the last stage, and gradually supervise the learning of picking affordance, providing value supervision for placing and picking affordance of previous stages. In this manner, we enable the model the awareness of future states, and thus avoiding the local optimal states. The above-described multi-stage training method requires multi-stage data for training. Randomly picking and placing to explore possible actions is inefficient and full of unsuccessful manipulations. Therefore, we propose a novel method to collect meaningful multi-stage data in a short time, named fold to unfold. We start from the target state, randomly fold the cloth by an action, and the reversed action with the corresponding manipulation result is collected as an unfolding action. And then we continue folding the cloth and collecting the reversed actions. Through this process, we could efficiently collect abundant unfolding actions and their corresponding results for learning. We evaluate our proposed framework on 4 representative benchmark tasks: cable ring no target, spread cloth, and rope configuration. Quantitative results and the manipulation sequences demonstrate that our dense affordance have the ability to facilitate manipulating deformable objects with complex states and dynamics, and outperforms other method. Also, with the integrated state values, our affordance could propose the global optimal actions. As we can see in the third row and the second column of manipulation action sequences, the agent chooses to place the cloth to the bottom right position. Although this action makes the current state have smaller coverage area, it facilitates following actions to fully unfold the cloth. Picking affordance and placing affordance in diverse tasks demonstrate our proposed dense representations have reasonable and abundant meanings, facilitating selecting, picking, and placing points for deformable object manipulation. As showed here, some states may have small coverage area but can provide more opportunities for future actions to fulfill the task. However, some states have larger coverage area but make the following actions hard to complete the task. Our learned values successfully reveal whether a state could facilitate future actions for the task. Compared with greedily trained affordance, our state value-aware affordance could select the global optimal manipulation, while greedy policy often falls to local optimal states. Our proposed method can be implemented in the real world. Here are some manipulation trajectories of our model in the real world. Please see the supplementary materials for more implementation details. Thank you for watching.